Swayam Prabha. Digital India. Educated India.
Welcome friends to this fifth lecture of module 2 of this environmental soil chemistry course, and in this lecture we will be talking about in details about different types of clay minerals, especially the secondary clay minerals. We have already discussed about the major clay minerals like 1:1 type of clay mineral like kaolinite, halloysite, and then we have talked about smectite like montmorillonite, illite, vermiculite, chlorite. And in today's lecture, we will be talking about other types of clay minerals which are present in the soil. So, let us first start with the intergrade clay minerals. Now, these intergrade clay minerals are basically intermediates between the vermiculite and smectite. You know, vermiculite is a kind of an expanding clay mineral, 2:1 type of clay mineral, and smectite or montmorillonite is a maximum swelling or maximum expansible clay mineral, and these intergrade clay minerals are somewhat intermediate between this vermiculite and smectite. And in this interlayers, in this mineral, the interlayer space has exchangeable cations and gibbsite like or brucite like island, but are not continuous like chloride. In case of chloride, what happened in that in between in the interlayer space of 2:1 type of layer, there is a continuous hydroxy interlayer, either it is a brucite or it is a gibbsite. So, here there is also a gibbsite or brucite like structure. However, the interlayer space as not they do not have the continuous gibbsite or brucite like structure. So, this is the characteristic of this intergrade type of clay mineral. Now, accordingly, the interlayer space does not collapse on heating as readily as with the smectite and vermiculite, but it does collapse more easily than that of complete interlayer hydroxy sheet in chloride. So, let us see how this interlayer space of this mineral basically looks like. So, if we move ahead and see, this is okay. So, example is hydroxy interlayered vermiculite in acid soil. So, this is an example of hydroxy interlayered vermiculite. You can see this is a vermiculite. In the vermiculite structure, this is a magnesium in the octahedral site, So, it is a 2:1 type of mineral. In the interlayer space, this is basically magnesium bound water as well as aluminum in the octahedral layer. So, it is basically here you can see the interlayer here is basically composed of the hydroxy aluminum layers. So, it is not a continuous layer, it is somewhat in discontinuous layer. So, basically you can see this is a illite structure, and when this illite interlayer potassium get replaced, then it basically converts into the vermiculite, and you know that in the interlayer space of vermiculite magnesium bound water is present, and when this magnesium bound water is also having adjacent hydroxy aluminum interlayers, aluminum hydroxy interlayer, then it is called hydroxy interlayer vermiculite. So, this is an example of intergrade clay mineral. Important source of aluminum in these soils, and also in alkaline soil these interlayer materials is basically hydroxy magnesium or magnesium hydroxy layer. So, if we move ahead and see another type of clay mineral called interstratified clay minerals. Now, interstratified or mixed layer phyllosilicates are structures in which the layers of more than one type of clay mineral stacked together within the crystal. So, they are usually metastable intermediate product on a sequence of reaction involving end member clay minerals. So, when one clay mineral converts to another clay mineral due to different types of reaction, these are metastable variant or metastable intermediate products, where you can see that different mixed layers are present. For example, 2:1 and 1:1 type of clay mineral, they have the strong interlayer bonding, but weak interlayer bonding. They have strong intralayer bonding. That means 2:1 layer has the strong intralayer, they have strong attraction. However, when they stack each other, stack upon each other, their bonding is relatively less. So, stacking, as a result of that, there is a stacking of different layers. So, example, interstratification of smectite with chlorite, and this is known as the Corensite. Also, when there is a illite with smectite, we call it rectorite. Also, we can see kaolinite with smectite. So, these different types of clay minerals layer, when they stack one above each other, then we get this interstratified clay minerals. The reason, again, although within this 2:1 type of layer the bond is strong, however, the interlayer bond is negligible. So, as a result of that, there is occurrence of stacking. Now, let us move ahead and see some amorphous minerals which are present in the soil. Examples are allophane and immogolite. So, these are basically clay sized minerals commonly associated with the volcanic ash type of soils, where there is sufficient moisture for silica to leach. It also occurs in some non-volcanic regions, but mostly they are basically occur in the volcanic region. Three major type of allophane is there: aluminum rich soil allophane, silicon rich soil allophane, and stream deposit allophanes. So, these are three major variants of allophanes which we can see in the soil. So, this is the how this allophane looks like. Basically, in this allophane, silica and alumina ratio is basically 0.82 to 2. It varies from 0.84 to 2. It is also similar to kaolinite. Aluminum is present in both tetrahedral and octahedral coordination and exhibits spherical particles with 30 to 50 nanometer diameter, and soils with allophane have significant organic matter and also allow low bug densities due to high organic matter. Now, another amorphous mineral is immogolite, where the silica alumina ratio is 1 and aluminum is present only in octahedral coordination. It exhibits thread like particles that are parallel tubes of 20 nanometer diameter, and it has the capacity to absorb monovalent cations like halloysite. Another type of clay mineral we can see in the soil are fibrous clay minerals. Just like here you can see it is a palygorskite, it is a special type of fibrous clay mineral. Now, it has, why it is fibrous clay? Because they have fibrous morphology and it is composed of ribbons of 2:1 type of phyllosilicates, and it does not have continuous octahedral sheet. So, these are the reason, that is why it looks like fibrous, and the ribbons are basically linked to each other by inversion of silica tetrahedra along a set of silica oxygen silica bonds. We will see in the next slide. And basically they require alkaline condition and they basically have high silicon magnesium activity for stability. So, basically they require alkaline condition for their stability. In the acidic condition they will degrade. So, as I am telling you, these ribbons are linked to each other by inversion of silica tetrahedra along the set of SiO-Si bond. Let us see. So, as you can see, there are different models of this palygorskite. As you can see, these is a 2:1 type of layer, this is another 2:1 type of layer. However, in this 2:1 type of layer, when this this is basically a silica tetrahedral layer and this blue is basically aluminum octahedral sheet. So, aluminum octahedral sheet is sandwiched between two tetrahedral sheet, and when the two tetrahedral sheet in the adjacent layer are joined together by sharing their sharing their oxygen, as you can see here, just SiO-Si bond. As a result of that, we will see this fibrous like structure. Now, depending upon their distance, they are of different variants. For example, you can see here the different B axis spacing is 1.806 nanometer. However, according to the Gard-Fortlet model, it is also 1.806 nanometer. However, the C axis spacing is 1.27 nanometer. This is another clay mineral called sapiolite. You can see here the distance is 2.68 nanometer, where the C axis spacing is 1.34 nanometer. So, this is how this fibrous mineral basically composed. Other important minerals which are present in the soil as a result of high weathering, high amount of chemical weathering, are different oxide, hydroxide and oxyhydroxides. So, oxides refers to the metal hydroxide, oxyhydroxides and hydrous oxides, and they have, you can see here the Gibbsite structure, that means it is dominated by aluminum. They have high specific surface area and reactivity, and they may exist as discrete crystals as coatings on phyllosilicates and humic substances and mixed gels. So, these are basically the end product of the intensive chemical weathering. Let us start with one, aluminum oxides or Gibbsites. Now, in the Gibbsite you can see it is basically most common, Gibbsite is most common, sorry, let me, I guess, yeah, it is the most common aluminum hydroxide mineral. It is found in highly weathered soils like oxysols and altisols, and it has two planes of closely packed hydroxyls with aluminum in between them. So, you can see here these are closely packed hydroxyl with aluminum in between them. So, it is a basically dioctahedral kind of structure, and the d-axis spacing is 0.48 nanometer. Okay. And in the interior, obviously these aluminum, as you can see, they are sharing their they are basically sharing with 6 hydroxyl ions in the interlayer. However, those aluminums which are present in the edge, they will basically share with only 4 hydroxyl ions. So, this is the shape of this is the structure of aluminum hydroxide or Gibbsite. So, if we move ahead and see iron oxide, the most prevalent iron oxide is goethite. It is basically composed of iron and oxygen. Octahedron is the basic structure of all the iron oxides, can be either alpha phase, that is hexagonal close packing, or gamma phase, which is cubic close packing. And so, isomorphous substitution sometime basically replace Fe3 plus with L3 plus and Mn3 plus with Cr3 plus. Okay. So, Fe3 plus sometime get replaced by either L3 plus or Mn3 plus or Cr3 plus. So, isomorphous substitution occurs in these iron oxides also. So, goethite, as I have told you, it is one of the most common and thermodynamically stable iron oxides. It is found in humid as well as in semi-arid regions. It is thermodynamically stable. It is basically needle shape crystals with the edge and grooves, as you can see from this structure. It is a needle shape with the with the edges and the grooves, has double bands of FeOH octahedra sharing edges and corners, as you can see in this structure, and also bands bonded partially by hydrogen bonding. So, this is the structure of goethite. So, another important iron oxide which is present in the soil is hematite. The hematite has the formula of Fe2O3, and it is the second most prevalent or most common iron oxides mineral in the earth crust after goethite. It is also responsible for red color of many soils. It is mainly found in highly weathered soils, as we have already discussed that these oxides are basically present in highly weathered soils because of chemical weathering, and also has FeO6 octahedra connected edge by shape. So, this is basically the structure of this hematite, where these red dots are showing the oxygen, whereas these blue dots are showing the iron. So, another important oxide is manganese oxides. Now, the manganese oxide are basically occurring as coatings on soil particles in cracks and veins as well as nodules. One example, major sources of manganese in the soil. Manganese, as you know, it is one of the major plant micronutrient, and these manganese oxides are one of the major source of manganese in the soil. Act as an oxidant for metals like either arsenic or chromium, and it is mostly amorphous, and examples are barnesite as well as pyrolusite. So, this is an example of pyrolusite, which is one of the most prevalent manganese oxide in the earth crust. So, apart from these all these oxide, intergrade minerals, interstratified minerals, primary 1:1 type of mineral, 2:1 type of mineral, 2:2 type of mineral, we also see carbonates and sulfate minerals in the soils. So, they are basically most prevalent in arid and semi-arid regions, and they are highly soluble compared to silica minerals, and they are unstable. Unstable carbonate minerals are examples are calcite as well as magnesite, and stable carbonate minerals are dolomite and siderite, where dolomite is basically calcium magnesium carbonate, whereas siderite is iron carbonate. And sulfate minerals, as far as the sulfate minerals are concerned, the most important one is gypsum, which is basically calcium sulfate dihydrate. So, these are some of the important carbonates and sulfate minerals which are present in the soil. So, let us discuss another very important thing, that is specific surface of minerals. Now, specific surface area is a property of solid defined as the total surface area of a material per unit of mass, and it is basically expressed in terms of square meter per kg of solid. So, secondary minerals, remember, they have high surface area because their size is very small. They are the end product of weathering, they are the end product of all type of weathering, both physical and chemical weathering. So, basically they have very small size, and the total surface area of the secondary minerals are basically given by the AC plus SI, where ST is basically the total surface area in square meter per gram, whereas the SI is basically the internal surface area square meter per gram, and AC is the external surface area, that is square meter in gram. So, the external surface area is determined by measuring the amount of nitrogen gas adsorbed by a surface at temperature near the boiling point of liquid nitrogen, which is 77 Kelvin. Now, surface analysis is surface area analysis is done based on the BET equation. Now, BET equation basically given by this name of these three scientists, Brunner, Emmett and Taylor. So, it is a BET equation. BET theory we will just learn in the next slide. So, depending on the surface area, we use different types of adsorbent. For example, if the surface area is greater than 10 square meter per gram, we will use the nitrogen. If it is between 0.1 to 10, then we will be using krypton gas. If it is less than 0.1 square meter per gram, we will be using ethylene. So, let us see how this BET theory explains this calculation of the surface area. So, this is the formula of BET equation, as you can see, P by V, P0 minus P, where this P is basically the pressure of gas at equilibrium with the solid, with the solid in Pascal, and P0 is the basically gas pressure required for saturation at the temperature of the experiment, that is also measured in Pascal. V is the volume of adsorbed gas adsorbed at pressure P in cubic meter. Vm is the volume of gas required for monolayer coverage over the complete adsorbent surface, and C is a constant which you basically calculate by using this formula, whereas E1 basically shows the heat of adsorption of the first layer of adsorbate, and E2 is basically heat of liquefaction of the gas, whereas R there is a gas constant and T is the absolute temperature. So, by using this formula of BET equation, we can calculate the monolayer adsorption of nitrogen. How? Let us see. So, if we we know this formula. So, once Vm is determined by the linear plot between PV versus P by P0, because we know if we if we go back to our previous slide, it will be clear that if we put if we draw a graph using these two, then this is basically the, if it is the dependent and this is if this is the dependent and this is an independent variable, if we consider this is basically slope and this is the offset. So, basically while drawing a graph, we can basically calculate these two terms, and from there we can calculate the Vm. So, once Vm is determined by linear plot between these two terms P by V into P0 minus P and P by P0, then the specific surface can be calculated according to this formula given by Hines, that is E equal to Na sigma multiplied by Vm by V0, where the E is the specific surface area of the adsorbent measured in square meter, and N is basically Avogadro's number, you know, which is 6.02 into 10 to the power 23 molecules per mole, and sigma is the cross sectional area of the adsorbent in square meter, V0 is the molar volume in cubic meter, and Vm is the volume of gas required for monolayer coverage over the complete adsorbent surface. So, this is how once we calculate Vm, we can calculate the specific surface area. Okay. Now, the specific surface area of different minerals, as you can see, it varies from one clay mineral to another clay mineral. In case of kaolinite, you can see it is varies from 7 to 30 square meter per gram, whereas in case of trioctadal vermiculite and also montmolybdenum, you can see it is varying from 600 to 800 square meter per gram, because of their high accessibility of the interlayers. Remember, in case of kaolinite, the accessibility of the interlayer is very less. There is no interlayer because the structure is collapsed and there is no space, interlayer space. However, in case of montmolybdenum, in case of vermiculite, there is huge interlayer space. As a result, the specific area is also higher in case of montmolybdenite and vermiculite as compared to kaolinite. Now, how to measure the total surface area? We also use the ethylene glycol monoethyl ether, we also known as EGME. Also, we use it commonly as an adsorbent for total surface area measurement. Now, excess of EGME is applied. How we measure that? We basically apply excess of EGME to the adsorbent which has been dried over a P2O5 desiccant in a vacuum desiccator. So, basically we put the adsorbent and then dry it in the vacuum desiccator in the presence of P2O5 desiccant, and then we put excess amount of ethylene glycol monoethyl ether or EGME. Then all except the monolayer is removed using a vacuum desiccator containing calcium chloride as a desiccant. So, when we remove the layers of this EGME, then we can plot the weight of EGME retained on the solid as a function of time, because as the time will pass, obviously the weight of the EGME which is retained on the surface will go down, and we can then determine when the weight of the EGME become constant. So, the monolayer coverage is assumed to be attained at this point when the weight of this EGME becomes constant. When it is reducing along with the time and becomes constant at a particular time, then we can assume that we are getting the monolayer coverage. Then the surface area is calculated according to this formula given by the scientist Carter et al., where A is the specific surface area in square meter per gram. Wg is basically the weight of the EGME retained by the sample after monolayer equilibrium. Ws is basically weight of P2O5 desiccant which we use to dry the samples before putting the excess amount of EGME, and basically we know that 2.86 into 10 to the power minus 4 grams of EGME is required to form a monolayer on 1 square meter of surface. So, once we get the total surface area, from that surface area we can also calculate the internal surface area by just subtracting the the external surface area. So, this is how we can calculate internal surface area, external surface area and the total surface area. The type of charges in the soil, you have also already know there are two types of charges already occur in the soil. One is called the permanent charge, another is variable charge. In case of permanent charge, it is always occurred through isomorphous substitution. As a result of isomorphous substitution, excess of negative charge developed, and this negative charge is known as permanent charge. This is a structural component, this is a structural characteristics. So, that is why it is called permanent charge. It is also known as the constant charge, and it does not vary. Why it is called a constant charge? Because it does not vary with the pH. It developed during the formation of the mineral. Another type of charge is there, that is called variable charge or pH dependent charge. So, it is basically occurred due to protonation and deprotonation of functional groups on inorganic soil minerals. It basically changes with the pH. So, basically at the age of the mineral, you know there are some hydroxyl groups are present. So, if the soil has high pH, obviously the hydroxyl groups will be more prevalent. As a result of that, one hydrogen or proton will go to meet with the excess of hydroxyl ions, producing a negative charge in the edge. So, that will produce a negative charge. Just opposite occurs in case of acidic soil. In case of acidic soil, there will be prevalence of H plus ion. These H plus will basically react with this OH and basically produce this positively charged OH2 plus. So, this is, you can see, it is variable from one pH to another pH condition. That is why it is called variable charge or pH dependent charge. So, another important thing is known as the cation capacities of secondary soil minerals. Cation capacity, the negative charge on the soil minerals is basically balanced by positive charge in the form of exchangeable cations, and cation capacity is the total capacity of the soil to hold the exchangeable cations. It is an inherent soil property and difficult to alter, and CEC determines the soil's ability to hold nutrients and also provides a buffer against the acidification. So, the soil which has more CEC will basically be considered as a nutrient rich soil, because it can attract more cations. So, clay fractions and organic matter have more CEC than sandy soils, obviously because of this negative charge development. So, if you see the difference of CEC for different clay minerals, you can see kaolinite has the lowest CEC, talc has also the lowest CEC of less than 1 centimole per kg. Kaolinite has also very low CEC, and in case of trioctahedral vermiculite as well as montmorillonite, you can see they have the CECs varying from 100 to 200 or 80 to 150 centimole per kg of soil, because of huge amount of isomorphous substitution which is going on in the structure of these clay minerals. So, kaolinite, basically CEC of kaolinite varies depending on the impurity present in it. If few impurities present, the CEC is as low as less than 2 centimole. As pure kaolinite has very less isomorphous substitution, almost no isomorphous substitution. Negative charge resulting from surface functional groups such as aluminum hydroxide. So, in case of kaolinite, then whatever negative charge is present is due to the pH dependent charge because of the broken edges and the hydroxyl groups which are present in the broken edges. So, in case of halloysite, pure halloysite has the little ionic substitution, hence lower CEC. It has association of halloysite with allophane, also increases its CEC. Also, exchangeable ammonium and potassium present in the interlayer results is inflated CEC measurements. So, if you see the vermiculite, obviously dioctahedral vermiculite has more layer charge than smectite, but less CEC due to presence of potassium, some amount of potassium present in the interlayer. And K plus has the smaller hydration radius, and that it is fits snugly. I have already told it is a very small, so it is fits very snugly in the interlayer space. And the attraction between the K plus and clay's interlayer surface is more, hence it is less available to exchange. And in case of trioctahedral vermiculite has calcium and magnesium in the interlayer, so more CEC than that of dioctahedral vermiculite, because they have no restriction for cation exchange. If we see montmorillonite, they have high CEC due to substantial isomorphic substitution and fully expanded interlayer. In case of mica, they have more layer charge than vermiculite, but lower CEC, and also due to presence of potassium in the interlayer space, they have lower CEC. Although they have low, more layer charge than vermiculite, they have low CEC because of the potassium in the layer space, because of the log structure. In case of chlorite, although there are some substitution occurring in the layers, however, due to the presence of the aluminum hydroxy or magnesium hydroxy layer log structure, the lesser CEC than expected can be found. In case of allophane, aluminum substitute silicon. So, lots of edge sites created, therefore, the CEC is very high. Like halloysite, absorption of other salts will also cause high CEC. So, this is a relationship between CEC and different types of clay minerals. One thing is very clear, that as we go from mild weathering condition to intermediate weathering conditions or strong weathering condition, cation exchange capacity goes down, and also the catenation capacity is highest in case of 2:1 type of clay, intermediate in case of 1:1 type of clay, and aluminum hydroxide and iron oxide, they have the lowest catenation capacity. Similarly, there is a negative inverse relationship between the catenation capacity and anion exchange capacity. As the catenation capacity decreases, anion exchange capacity increases, because in those minerals which have low catenation capacity, they have more pH dependent charge. So, as a result of more pH dependent charge, they produce some anion exchange capacity. So, this is the relationship between weathering, CEC and AEC. So, d-axis spacing, you can see that it is another important aspect of differentiating different types of clay minerals. We will be discussing this in details in our future lecture, in our lectures in the last week, that is while we are discussing about the module 12, how we can use the X-ray diffraction to calculate this d-axis spacing. Now, d-axis spacing varies from one clay mineral to another clay mineral. It is lowest in case of kaolinite, however, it is highest in case of smectite, also it is high in case of vermiculite. So, the d-axis spacing is the basis for differentiating one clay mineral to another clay mineral, and we can use the X-ray diffraction technique to differentiate different types of clay mineral. So, this is the gist of X-ray diffraction analysis. This X-ray diffraction analysis shows that there are different layers of atoms. In these different layers of atoms, at repeating layers of atoms, the distance is called the d-axis, d-spacing. So, if we use the X-ray diffraction analysis, this is the one incident X-rays, this is another incident X-ray, this is another incident X-rays. So, when the X-ray hit one plane, it get diffracted. So, this is diffracted X-rays. So, there is a term called constructive interference and destructive interference. When two waves are in phase, we call it, they create this constructive interference, as you can see, and when they are 180 degree out of phase, they are producing the destructive interference. This is the example of destructive interference. So, one thing is clear, that to create a constructive interference between these two rays, diffracted rays, the distance, it generally follows the Bragg's equation. So, it shares the Bragg's law says the two rays. So, if it is considered ray 1 and this is considered ray 2, the two rays will constructively interfere. So, they will basically constructively interfere if the extra distance ray 1 travel is a whole number of wavelength farther than what ray 2 travels. So, let us consider this is the ray 1 and this is ray 2. So, you can see the extra distance this ray 1 travel is this BC plus CD as compared to the ray 2. So, this BC and CD can be calculated. So, BC plus CD is basically n lambda. So, basically it is a whole number of wavelength further. So, if we consider the wavelength of the X-ray is lambda and it is whole number so, whole number we can calculate by n lambda, n is an integer. So, the extra distance, it is calculating BC plus CD, we can calculate that BC plus equal to CD equal to d sin theta. So, BC plus CD we can see here, it will be 2d sin theta. So, n lambda equal to 2d sin theta. So, this is called the Bragg's equation, and based on Bragg's equation we can calculate, if we know this if we know this theta, if we know this n, if we know this lambda, we can calculate this d-axis spacing, and from this d-axis spacing we can identify, okay, this is the clay mineral. For example, different clay minerals have different types of d-axis spacing. For example, kaolinite has less 7.2 angstrom or 0.72 nanometer. You can see these are the X-ray diffraction peaks of kaolinite at first order diffraction peak, and this is the second order diffraction peak. So, this is how we can identify different types of clay minerals through X-ray diffraction. For X-ray diffraction, we do different types of pre-processing of the soils, all those are mentioned here. What type of what type of pre-processing we do here. Also we prepare different types of slides for processing, and we process these clays. We orient these clays in the glass slides, and then we saturated them with either potassium or magnesium. Excess salt are removed with water, and different types of treatments are given. So you can see there are different types of treatments: potassium saturation, magnesium saturations, and also different temperature, and how this different temperature varies their d-axis spacing. So from there you will have an idea. If you have this table in front of you, and if you see those peaks from the X-ray diffraction, you can identify, okay, we are seeing this peak at this point, so obviously this will be the peak of either mica, either kaolinite, either montmorillonite. So guys, this brings the end of this module 2. We have discussed in details about the different inorganic components and clay minerals, different types of other secondary minerals, how they can be differentiated. This is the reference of this chapter. There is Environmental Soil Chemistry by Donald L. Spark. You can get more information from this book, and hopefully you have learned some new information from this lecture. And please feel free to email if you have any questions. I will be more than happy to answer your question. Thank you.